Hey everybody, I want to talk to you real quick about figuring out the thermodynamics of solutions. This is something we've been talking about for a while and I'm still seeing a lot of confusion around it. So I just wanted to give this additional opportunity for you to understand. The first thing we have to do when we're thinking about the thermodynamics of solutions is we have to figure out what type of solution are we making. And there are a couple options we have here. The first thing we should look for is, are we looking at a covalent solution? That's going to be a situation that's dominated by intermolecular forces. And that would be like dissolving water and oil together. My classic example is making a salad dressing. The other category that we typically talk about in this class is when we are doing a solid ionic compound. This is where we're going to be looking at lattice energy. And in both of these cases, we can look at the process of forming the solution by mixing two things together, or we can look at the process of separating the solution. Thermodynamically, those should be opposites of each other, but we'll see that with some examples. In either case, we're going to have the same type of situation for delta H of solution. And that enthalpy of solution is going to be the enthalpy of the solute plus the enthalpy of the solvent plus the enthalpy of mixing. And there's a couple things we know about these particular terms. Step one here is the process of making space between the solvent molecules. This is always an endothermic process, right? So this would be taking our water molecules and making space between the water molecules so we can fit things in between them. Step two is also always endothermic. That's the delta H of solute. And that is going to be making space between our solute molecules. Whether this is covalent or ionic, we're making space between the solute molecules. So in both of these situations, we know the delta H of solute is positive. We know the delta H of solvent is positive. The delta H of mixing is this last step where the two things get mixed back together. We're going to be looking at the interactions of the solvent particles with the solute particles, and that will give rise to some exothermic process. Now, we know that third step is always going to be exothermic, but you can notice with these two pictures on either side, we don't know if it's going to be more exothermic than our endothermic steps. Generically, we can't say. When we start looking at specific cases, we'll start to see that there are times when we can specify what's going on. So we always know this delta H of mix is negative. We can do the same type of thinking with our delta S of solution. Where again, we're going to have our delta S of solute. We're going to have our delta S of solvent. And we're going to have our delta S of mix. Again, looking at this picture, we can see that the process for making space between the solvent and making space between the solute, those are both going to be an increase in entropy because we're pushing particles away from each other. We're giving them more ways to rearrange. So these first two are always an increase in entropy. And the last one is always a decrease in entropy, right? Whenever we start putting things back together, we start trapping them into different positions. That's always going to be a decrease in entropy. And again, at this point, we can't generically say which are bigger, the two positive terms or the negative term. We can say they're positive and negative, but without particular cases, we can't say what's going on. So let's go ahead and look at a particular case. Right? And almost always when we start these problems, the first thing it asks us is, what's the delta G of solution? Now, the delta G of solution is something that we know we can figure out from delta H and delta S. But we can also determine delta G by doing experimental observation. If we see two things mixed together without putting extra energy in, that's going to be a spontaneous process. That's going to be product favored. That's going to be a process where we know delta G is negative. If we put a solid into water and we see that solid dissolve, right, that physical observation tells us that the process of that solid dissolving is spontaneous. If we put two liquids together and we see a solid form, we have that situation where we physically see a solid form. That means the formation of this solid is spontaneous. If we mix two liquids and we see them separate, we know that the process of the mixing is not spontaneous. Right? They'd rather be separated from each other. So there's all these different cases where we can have experimental observation, and we can say something about what's happening with the solute, solvent, the mix, the delta H, the delta S, in those particular cases. And the part that helps us do that is having that experimental observation of delta G. Let's look at a specific case. So the most common case, the one that we started with at the beginning, was dissolving a solid in water. I'm going to go ahead and pick sodium carbonate. And when I put this into water, it's going to break into two Na pluses and a CO3 minus. Now, because we're looking at this specific case, there are some specific things we can say about delta H's and delta S's. The first thing that we can realize is we can put our terms together for our delta H of solution. And we can say, look, in this situation, it's not just any solute, it's specifically a delta H of a lattice. I'm taking this solid material that has a crystal lattice and I'm breaking it apart. So if we're looking at ionic solids, our solute is always going to be that crystal lattice term. Our delta H of solvent is always water in this case, the cases we're looking at this quarter. And our mixing is going to be the process of these ions, this sodium ion and this carbonate ion, being surrounded by water. And so we call that combined process the delta H of hydration. Now, this isn't really doing anything different than we've already done. All that's happening is I'm putting these two terms, the delta H of solvent and the delta H of mix, together for this particular situation of dissolving a solid in water. The other thing that's interesting about this case is the delta H of hydration, because this solvent term is just dipole-dipole interactions, right? If we're looking at just water, the delta H of solvent is always from dipole-dipole interactions, and the delta H of mix is from ion-dipole interactions. In this situation, again, this particular situation of dissolving a solid in water, we always know that the ion-dipole interaction is going to be stronger than the dipole-dipole interaction. That gives us something specific we can say. In this situation, where we knew that the delta H of solvent was positive, the delta H of mix was negative, the mixing term for this particular case is always going to be larger. So we can say the delta H of lattice, again, is always positive, but because we have these specifics we can say, and I'll draw it kind of in a cartoonish way. My delta positive is smaller, my delta negative is bigger, so this delta H of hydration is overall going to end up being a negative term. It gives us, the reason we do this is because it gives us two terms to talk about instead of three terms to talk about, and it makes it a little bit easier to do the processing. So now, if we could figure out what was bigger, the lattice energy or the hydration energy, we could figure out what the delta H of solution was. This is where you have those problems where they specifically say the absolute value of lattice energy is more than the absolute value of hydration energy. And this could be flipped. It could be more than, could be less than. Sometimes they say hydration first, sometimes lattice first. But because we're in this particular case of a solid dissolving in water, we can specifically say, look, we know if the absolute value of lattice energy is more than the hydration energy, this thing is a bigger positive than this thing is negative, my delta H of solution is going to be positive. If we switch this statement, we of course also flip our sign of the delta H of solution. In the past, when we did this experimentally, we actually just measured the delta H of solution. We stuck a thermometer in as we dissolved solids and we saw the temperature go up, which would be an exothermic delta H of solution, or we saw the temperature go down, which would be an endothermic enthalpy of solution. So again, we can do this through information provided, or we can do it through experimental observation. The fact that we picked something that is soluble allows us to say a particular piece of information, right? A positive delta G, that would tell us something would stay as the reactants. And for this particular case, that would be an insoluble situation. Delta G less than 0 would tell us if we instead form the products. And I like to think about this particularly as staying as reactants or forming products, because the thing that becomes important here, when we say stays reactants or form products, the thing we need to think about goes back to this very first step of what actual solution are we making, right? This first idea of what solution are we making, is it covalent solution, ionic solid? Are we forming a solid? Are we dissolving a solid? Are we mixing two things? Are we separating two things? Whichever case I'm looking at, delta G will be positive if it stays on the reactant side, and delta G will be negative if it goes towards the product side. And so the question becomes, well, what am I looking at? In this particular case, I'm looking at a solid becoming ions in solution. I have this experimental observation that tells me it becomes ions in solution. So I can go ahead and say, oh, in this case, where I have the experimental observation of products forming, I know my delta G. I know my delta G is negative. At this point, we can go ahead and do the last thing and figure out the logic of what's happening with our entropy. Now, one of the funny parts is most people assume that if you're breaking apart a solid into water, that your entropy is increasing. But remember, you're breaking apart the solid, you're breaking apart the water. Those are both increases in entropy, but when we mix them back together, that's a decrease in entropy. And just like the delta H, we don't know if the decrease in entropy is going to be bigger or smaller than the increase in entropy. So in this situation, we have to use a little bit of logic. There are cases where we can say something specific about the entropy, but generically, we usually just kind of use the two things that are easy to experimentally observe, the delta G and the delta H, and then make some logical statement about the delta S. So in this situation where we saw the delta G was negative for the particular case we're looking at, and we saw the delta H was positive, if we're considering this first situation, we'll call this situation 1. This will be for situation 1. The delta H is positive. This means the only way this works out is if delta S is positive. In this situation, what we need is this overall negative T delta S term to stay negative, so the delta S has to be positive. Right? We can't say which part is causing it to be positive. Right? When we look at this equation, we don't know if it's the solute part or the solvent part, but we know those two parts together are larger than the mixing because the increase in entropy overall for the solution stays positive. Now, this was just looking at one particular case. There are, of course, lots of different cases that we can look at, but if you follow this logic, you should be able to think about all of the different possible cases. Depending on which situation you're looking at, your delta H of solution might change. Your delta H of lattice, your delta H of hydration might change. Again, if we flipped this reaction, we would flip our delta H values. So we have to pay attention to which reaction we're actually looking at, which process. And again, if we were, instead of looking at this case of ionic solids, if we were looking at covalent solids, that would also change it. We'd have to consider the intermolecular forces more carefully.